Good morning. I'm Chetna Singhal, and I'm presenting our paper on resource-aware deployment of dynamic DNNs over multi-tiered interconnected systems. This work has been done in collaboration with Yashua, Francesco, Professor Marco, and Professor Carla. In our work, we have used dynamic DNNs, which are dynamic deep neural networks that empower diverse applications with complex data analysis and decision making. These applications include computer vision, speech recognition, natural language processing, and mobile healthcare. These models, however, are highly complex and require high amount of energy consumption in the training and inference computation stage. There are technical strategies to deal with these challenges, which include model compression, where techniques like model pruning and quantization is used. A second strategy is to use edge computing, wherein the execution is offloaded at the network edge. We can also use split DNNs, which help us in dynamically controlling the computation and communication on device and server links. Recently, there's an introduction of dynamic DNN architectures, which includes early exits. In our work, we use dynamic DNNs with early exits. Here in this example, the figure shows branchy AlexNet model. The architecture here consists of 5 backbone DNN blocks, 2 of which constitute the head part of the model, and 3 such backbone blocks constitute the tail part of the branchy AlexNet model. There are 3 exits. Exit 1 and exit 2 are the early exit branches. Exit 1 is deployed on the head, and exit 2 is deployed on the, along with the tail on the edge device or the edge node. And the exit 3 is also linked to the tail and deployed on the edge server node. Here in this figure, we show 2 applications. Application 1 deploys the machine learning model with early exits on the mobile nodes, edge server nodes, as well as the cloud server nodes. Here, the application 1 has the early exit 1 computed on the mobile node itself. Early exit 2 deployed on the edge server node gives us the early exit at the edge server node point, and the final output can be obtained at the cloud server node. Whereas the application 2 only uses the mobile node and the edge server node, the early exit 1 is deployed on the mobile node, and the output from early exit 2 is obtained on the edge server node. Here, the communication between the mobile nodes and the edge server nodes, as well as the edge server nodes and the cloud server nodes, is for the tensors between the DNN blocks that are deployed on each of these different type of nodes. Our objective is to orchestrate the machine learning model with dynamic decisions on which part of the DNN should be activated, which data source should be used, and what should be the sampling rate set for the particular application, where should we deploy the DNN layers in the cloud edge Internet of Everything continuum, and the split configuration that should be selected with the early exits. Overall, we aim to meet the application requirements in terms of inference quality, that is the accuracy and inference latency, while minimizing the overall energy consumption. This entire optimization problem is listed here with an objective to minimize the energy consumption by finding the best machine learning orchestration configuration. This is subject to constraints in terms of inference latency, inference accuracy or quality, as well as the system level resource constraints in terms of the computation and the communication resource. In the top figure on the left side, we have shown the two-dimensional two-plane system model that we use to define the system, wherein one plane consists of the network nodes and the interconnection between these network nodes. And the second plane has the DNN architecture with early exits. And overall, we map this to a one-plane extended graph. Now, in the one-plane extended graph, we have the vertices defined as the DNN blocks deployed on a particular network node, and the interconnection between these vertices, that is the edges in this one-plane extended graph, depend on the DNN model architecture and the feasible deployment configurations, uh, which are mapped to the corresponding vertices in the one-plane extended graph. Finally, we obtain a feasible graph from this one-plane extended graph, which I will explain in the next slide. Since the optimization problem shown in the previous slide is NP-hard, we have developed a heuristic solution which we call as feasible inference graph. The steps of the feasible inference graph are summarized in the block diagram shown here in this slide. The input taken here is in terms of the DNN model architecture, which is denoted as layers. The network architecture, which is denoted as nodes, and the application constraints that we need to meet in terms of accuracy, latency, as well as the system resource constraints. Using the layers in the nodes, we first create the system model graph, which we further map to a one-plane extended graph. And using a heuristic solution, that is the FIN approach, we devise the feasible graph and we obtain the shortest path from this feasible graph, which gives us the efficient solution or the efficient machine learning orchestration that should be used in the given system to meet the objectives as well as the constraints. So the feasible graph actually summarizes all the feasible solutions guaranteed through the additive constraint, which is the inference latency by the graph topology itself, and the system capability and application requirement constraints in terms of quality and bandwidth by pruning the violating edges and vertices. Specifically, this feasible graph for the example that we considered is shown on the right side of the figure shown in this slide. Here we use a parameter gamma, which is the resolution of the feasible graph or our heuristic solution. In this example, we consider gamma equal to 5, and here specifically what we do is the one-plane extended graph vertices are replicated gamma times, and the interconnection between these vertices in the feasible graph depend upon the additive constraint and the system capability and application requirement constraints being met. So here what we specifically do is we use the gamma, which is the resolution of the feasibility graph, and each vertex in the extended graph is replicated gamma times. So specifically, the heuristic solution's complexity depends on gamma. Higher the value of gamma that we use, higher is the complexity of our heuristic solution. For the performance evaluation, we consider 3 dynamic DNNs with early exits. That is branchy AlexNet, branchy ResNet, and branchy LeNet. Each one of these uses different data sources, and the architectures considered are summarized in the DNN model specifications table. So BAlexNet and BResNet have 5 DNN blocks and 3 exits, while BLeNet has 3 DNN blocks and 2 exits. The network configuration consists of mobile edge and cloud nodes with the power, traffic, and energy specifications that is summarized in the table here. And we consider 6 applications, which is a combination of these DNN models that are considered along with different type of data sources. And correspondingly, we have different accuracy levels that are obtained at different exit points, which are summarized in this inference accuracy table. In order to see the impact of deployment configuration, we study the 3 configurations for the AlexNet and the DSNet. In configuration 1, we have all blocks deployed on the mobile. Configuration 2 has the blocks deployed along with the exit points on the mobile and the edge nodes. While in configuration 3, the blocks of the exits are deployed on the mobile edge as well as the cloud nodes. We study the performance in terms of inference latency and energy consumption, along with the accuracy for the corresponding applications. We can see that in terms of inference latency, each of these configurations has a different inference latency resulting based on the deployment for that configuration. So when everything is deployed on the mobile itself, inference latency is considerably high. Whereas if we consider the energy consumption for this configuration, it is much lesser than the other 2 configurations. While if we consider the second and the third configuration, its inference latency is much lesser, but the energy consumption is higher than the configuration 1. And this is because the energy consumption is not just for the computation, but also the communication of the tensors between the nodes of the network over which the deployment of machine learning model happens. So this tells us that dynamic selection of the configuration and the decisions thereof can actually impact the performance in terms of inference latency, energy consumption, and accuracy. Furthermore, we study the performance of our proposed heuristic solution, that is FIN, with respect to the optimal as well as the state-of-the-art benchmark multi-constraint path selection scheme. And the results are shown here in these figures. So for the optimal solution, we perform an exhaustive search. And since this is a simple scenario consisting of only the applications for the branchy AlexNet model, the exhaustive search gives us the optimal solution for this small scenario. And we see that the FIN solution with 2 different resolution parameters, that is 3 and 10, give us a performance between the optimal and the benchmark MCP scheme. So when gamma is higher, that is a higher complexity FIN solution has a performance closer to the optimal in terms of the energy consumption. That is the configuration selected using the heuristic approach for gamma equal to 10 is matching with the optimal solution. While for a lower resolution or a lower complexity FIN, the performance is better than MCP and between the optimal and the MCP scheme. Since it is not possible to find the optimal solution for a large-scale scenario consisting of multiple applications, we have compared the performance of our proposed FIN solution for gamma equal to 10, that is the resolution value, with respect to the state-of-the-art benchmark MCP scheme. We find that the energy consumption, both in terms of computation and communication, and the combined total energy consumption is much lesser for MCP, is much lesser for the FIN solution as compared to the MCP, and that is shown in terms of the energy consumption gain here. In terms of the failure probability, the benchmark has a failure probability greater than 0.2, while the FIN solution has the failure probability always lesser than 0.05. In terms of the deployment of the DNN blocks on the mobile edge and the cloud nodes, we find that the FIN solution balances the deployment of the blocks and the exit points on the mobile edge and the cloud nodes such that the energy consumption is minimized in a more balanced manner as compared to the MCP. In terms of the 6 applications considered, the exit points that are invoked in the configurations that are selected are highlighted in this figure, and we find that the FIN solution dynamically selects the exit point by meeting the application's requirements while also achieving energy consumption rate. Overall, the FIN scheme allocates the dynamic DNN sections to the mobile edge cloud nodes, and it uses a multi-stage graph modeling approach to minimize the inference energy cost. It matches the inference target requirements to constrain nodes' resources. It is low complexity, yet effective solution strategy that closely matches with the optimum. It consumes 65% lesser energy than the benchmark weighted multi-constraint path selection scheme, and it has lesser time complexity than optimal exhaustive search-based method. In the future work, we aim to optimize the bandwidth and computational resource allocations across different DNN-based applications in a multi-tier system. Thank you very much. Please share your comments, remarks, or questions at the email ID that is mentioned here.